we're going to dive into storm interactions, which can play a major role in the types of hazards you can expect from supercells and can give you a clue as to which storm you should target or reposition for during an active storm chase. Much of this will be based on new research on storm interactions by Cameron Nixon and others. If you'd like to do some digging on your own, head over to the articles you see on your screen here. In environments with strong deep layer wind shear and or relatively dry air aloft, storm interactions are critical in allowing nascent updrafts to survive early on in their life cycle. Strong deep layer wind shear can be detrimental to purely isolated updrafts, causing them to fizzle out before they can become robust. On the same token, isolated young updrafts that ingest drier air aloft, a process called dry air entrainment, can experience less instability than what may be measured in the environment, allowing them to become pinched off and struggle to reach maturity. However, updrafts can overcome these issues by clustering together initially. The interactions that take place during this clustering phase can yield wider, more sturdy updrafts that withstand strong vertical wind shear and dry air aloft. Often, this progression results in one or two dominant supercells after the initial interactions are complete, so even though early clustering may give the appearance of a more messy storm mode, remain patient and wait for the interactions to work themselves out.
Seats are currently on sale for our 2027 Storm Chasing Tour. Secure your seat now for this once-in-a-lifetime experience. Link in the description.
For example, let's take a look at the convective evolution in southern Mississippi during the April 12, 2020 tornado outbreak. 60 to 70 knots of 0 to 6 kilometer shear was in place, which is quite strong. Notice how the initial evolution of the convection coming out of Louisiana was extremely messy. This was the result of numerous updrafts clustering together. However, this aided in storm intensification in the face of strong vertical wind shear. Eventually, two discrete supercells emerged after the initial interactions were complete, both of which became significant tornado producers. Had the initial updrafts been more isolated in nature, they likely would have struggled, and the outcome may have been quite different. Storm interactions remain crucial in convective evolution after storms mature into supercells. In order to produce tornadoes, a supercell needs to achieve a balance of inflow and outflow. Too much inflow and the residence time of vortices underneath the storm's updraft decreases. Too much outflow and the mesocyclone gets persistently undercut by cold air. Both of these scenarios are detrimental to tornadogenesis. The amount of inflow that supercells in a given environment may have can be determined using a proximity hodograph. For those who aren't familiar, a hodograph is a plot of the wind speed and direction at each level of the atmosphere. We can draw a vector from our estimated storm motion, given by this black bullseye here, to the lowest point on our hodograph, which represents the surface. This vector illustrates our storm relative inflow. The longer that vector is, the more storm relative inflow supercells may have, and the more outflow that'll be needed to balance out the inflow. In this example, storm relative inflow was near 50 knots, which is very strong, so a lot of outflow would be needed to achieve the balance. In contrast, this environment features a very small storm relative inflow vector with a magnitude of about 20 knots, meaning that only limited outflow is necessary to achieve the balance. Now the question is, where does this outflow come from? Auxiliary storms near the rear flank of the supercell. As shown in their plots of the density of convection in proximity to a hypothetical supercell, Nixon et al. 2024 found that in cases of significant tornadoes, the amount of auxiliary convection near the rear flank of the storm tends to increase in the time leading up to tornadogenesis. In contrast, for non-tornadic cases, secondary maxima in convection tend to be situated near the left and forward flanks of the supercell. In these scenarios, outflow from left and forward flank auxiliary convection tends to undercut the main supercell, throwing off the inflow-outflow balance in favor of outflow, which is unfavorable for tornado production. This dispels the common practice in storm chasing of targeting the most isolated supercell at the tail end of a band of supercells, colloquially called the tail end Charlie. In a pair of supercells, the lead supercell tends to be tornadic, while the trailing supercell generally produces mostly hail. The same holds true for a cluster of supercells. The lead storms are most likely to be tornadic, while the trailing storms are most likely to be mostly hail producers. Within a QLCS, supercells at the head or north end of the line are most apt to produce tornadoes, as are any embedded supercells within the line, while the tail end supercell tends to produce mostly hail. The stronger the storm relative inflow, the more rear flank auxiliary convection is needed to achieve the inflow-outflow balance. Often, the outflow from these auxiliary storms doesn't directly influence tornadogenesis in the main supercell, but rather perturbations in the near-storm environment aloft induced by the auxiliary storms can be enough. On rare occasion, purely discrete supercells can produce tornadoes without any assistance from auxiliary storms, fueled only by the ingredients available within the ambient environment, but in the vast majority of cases, auxiliary storms are necessary. Let's take a look at some radar data of the multitude of storm interactions that can aid in tornadogenesis in supercells. The first is the classic merger, in which an auxiliary storm merges into an established supercell. Storm chasers already monitor for these mergers closely as they're known to frequently induce tornadogenesis. They lead to the widening and strengthening of the main supercell's updraft and can increase outflow production to achieve the inflow-outflow balance. Mergers include a right-moving supercell colliding with another type of convective object, including a small shower or non-supercell storm, a left split from another supercell, or a QLCS. They can also include two or more right-moving supercells merging together to create one conglomerate supercell, as in this example here. In this case, the original supercell may hand off to the merging supercell, which then becomes dominant. The merging supercell takes on the conditions that the original storm was experiencing, leading to rapid intensification and, often, tornadogenesis. The next type of interaction involves feeder cells. As their name suggests, these cells persistently feed into the rear flank of the supercell. Feeder cells can consist of only a couple trailing storms, or a whole line of storms as in this example here. As we discussed earlier, the degree of storm relative inflow dictates the quantity of feeder cells that's necessary to achieve the inflow-outflow balance. Perhaps the most subtle of all storm interactions is the nudger. A nudger is a cell that moves into the vicinity of the main supercell's rear flank, sometimes not even fully interacting with it. In some cases, even a small shower can be enough to nudge a supercell toward tornadogenesis, particularly in environments with weak storm relative inflow. Nudgers can also come in the form of a nearby supercell or a full-blown QLCS. Notice how the supercell undergoes significant tornadogenesis as the QLCS approaches. On occasion, when two supercells interact, they can undergo the Fujiwhara effect, which is when two vortices rotate around each other, often merging into one. This phenomenon is most prevalent in hurricanes, but the mesocyclones of two interacting supercells can sometimes orbit around each other, particularly when the storms are large and slow-moving. When this happens, the lead supercell tends to slow or move rearward toward the trailing storm while weakening, while the trailing storm accelerates or moves forward as it strengthens. Sometimes the two supercells can merge into one after the Fujiwhara is complete, which can induce very large hail production or significant tornadogenesis. Supercells undergoing a Fujiwhara can pose great danger to storm chasers in close proximity to the storms, including erratic tornado motion, so always use extra caution when chasing two supercells in close proximity to one another.
Remember to check out those links in the description below, and then watch another video.